let's talk about the approximate total distance in the way we were thinking about it before. We were saying take like delta xi, like the first delta x, the second delta x, etc., square it. Take the similar y delta x, delta yi, take the square root of all of that, and then add it all up. So we could say take the sum I equals 1 to n if you have n data points. And that worked great for a data set, right? But what if instead of a data set, we have a mathematical formula for some kind of curve? Like f of x equals x squared, or something fancier. Since we know how to solve the problem with data, and we don't know yet how to solve it with a formula, what if we turn the formula into data? Just take data from the formula. So we could say, let's have x be 7, and then 7.1, and then 7.2, etc. It doesn't matter what the y values are here, just whatever the formula tells you. That seems like a plausible thing if you wanted to take the arc length starting at 7, right? But what would be a better thing? Well, what if I took x and y data, but instead of going 7, 7.1, we went 7, 7.01, 7.02, etc. Do you think I would get a better estimate of the total arc length? I think that would be better, right? So what we're talking about here is taking data more rapidly, shrinking the step size. So we're basically saying let delta x go to 0, right? That would be the ultimate in small steps of a basically 0 step or infinitesimally small. And let delta y go to 0 as well. And what do we tend to call delta x and delta y when we're kind of sending them to 0? We tend to call them dx or dy. And once we're talking about dx's and dy's, we don't tend to talk about a summation anymore. We tend to talk about what? An integral sign. So we're going from our discretized version back to a more continuous view. So we're going to turn the summation sign into an integral. So our formula for arc length right now would be the integral of root dx squared plus dy squared, because we had basically delta x squared plus delta y squared. And here I'm not even going to put a dx or dy out here because I've already kind of got them in there. I know it's not quite proper integral notation, but let's live with it. And this fundamental idea will actually come up later in the semester when we talk about arc length for other kinds of functions where we've got x and y operating in different ways. So that's why I like highlighting it here. It's a more general point of view. But we're not used to not having a dx or dy out here, right? So let's work on transforming it into that. What I could do, and this might seem a little silly, I want to get a dx way at the back here, so let me factor a dx out. So I'll have a 1 here, and then a dy squared over dx squared times dx squared. Do you agree that if I multiplied this dx squared back through, it would cancel the dx here and leave me with dy like that, and the dx squared here times that 1 would give me the dx squared there? I really mean put this in parentheses. Okay, so now that I have a dx squared inside a square root multiplying the other stuff, what can I do? I can say, well, I'll copy that stuff. And in fact, I can turn this dy squared over dx squared into squaring like that. Put the square root like that. And then the dx squared, let the square root cancel the square and multiply by dx out there. Now it's looking like a more typical integral, right? And now let's think about what is dy over dx. That's another name for a derivative. So we can rewrite this if we want as the integral of, let's do big old square root 1 plus f prime of x squared dx. So that is the arc length integral that we'll be using in this chapter. So let's think about what's going on here. We're saying, and it's important to remember order of operations here, take the derivative, square it, add 1, take the square root, and integrate. Phew. Really what's going on here is this. It's just kind of simplified in some sense to a form that we're more used to. But like I said, later in the book, we'll come back to it in this form, and that's where it kind of matches the table calculations more intuitively. Oh, one thing I forgot to mention, we really want to emphasize here, this is not the second derivative. This is the first derivative squared. So let's write that here. So it kind of looks like that notation for the second derivative with d squared y over dx squared, but we're not doing second derivatives. We're just doing first derivative and then squaring that. We also are not squaring the function, then taking the derivative.